Now let's see how we can use the remainder formula. In example 10, we found the third order approximation to the function y equals the square root of 1 plus x for x around 0. How precise was that approximation? One way of determining the precision is to determine the maximum error associated with that approximation. How do we do that? We look at the remainder term and we find its maximum value. We want to find the remainder for the third order approximation for y equals the square root of 1 plus x around x equals 0, and then find the maximum value of that remainder, and that'll be the maximum error for our approximation. The general form of the remainder is this. Let's go through the terms here. For an nth order approximation, the remainder is n plus 1, so that gives us this coefficient here. It'll be the n plus 1 derivative of the function that we're looking for. And again, we have x to the power n plus 1. This formula gives us the remainder for the approximation for x about 0, in other words, a Maclaurin series. If we had a Taylor approximation around some number other than 0, then we'd replace the x here by x minus a to the n plus 1. However, the textbook just focuses on the Maclaurin series for approximations about x equals 0, so we'll stick with that. The z here is a value of x that we determine, and that's the value of x that maximizes that n plus 1th derivative. Let's look at how we determine z and say the maximum error for the third order approximation. For a third order approximation, n is equal to 3, so of course n plus 1 is equal to 4. The remainder then, r4 of x, is equal to 1 on 4 factorial times the fourth derivative of x evaluated at z times x to the 4. For the function 1 plus x to the half, the fourth derivative is equal to minus 15 on 16 times 1 plus x to the power minus 7 on 2. This is the stage where we determine z. We want to find the maximum of the absolute value of the fourth derivative. What determines the size of the fourth derivative? It changes as x changes. This is equal to minus 15 on 16 times, 1 over 1 plus x to the 7 on 2. As x increases, the second term will decrease, so we're dividing by a larger number. I think we can see that the fourth derivative has maximum value when x equals 0, since it gets smaller and smaller as x increases. The maximum value of the fourth derivative then is equal to the absolute value of minus 15 on 16 times 1 plus 0 to the minus 7 on 6. That's equal to 15 on 16. That's equal to m. The maximum error was given by this formula. So we found z, and we're replacing the fourth derivative with a particular value m that maximizes the remainder. For our third order approximation, we'll have, we can substitute in there, we'll have 15 on 16 times 1 over 4 factorial times the absolute value of x to the fourth power. That's equal to 5 on 128 times the absolute value of x to 4. Now we can find the maximum error for the approximation in example 10. We had x equal to 0.05. We substitute in for x. That will be 5 on 128 times 0.05, or the absolute value, to the power 4. And that's equal to, it'll be 0 and 6 more zeros, 2441. Or in more succinct notation, 2.441 by 10 to the minus 7. That's the maximum error, so our third order approximation was quite precise.